Today, Miss Gill and I are going to give you a lecture on gas laws. Gases occupy space. They have a volume. They exert a pressure, even if they are invisible gases. Let's look at pressure. Pressure is measured in several different units. Let's relate them to each other. 1 atm, or 1 atmosphere, is equal to 760 torrs, which is equal to 760 millimeters of mercury, 101,325 pascals, or 101.325 kilopascals. That's a metric conversion, right, between pascals and kilopascals. We can also measure it in PSI, which is pounds per square inch, and atmospheric pressure, the conversion factor would be 14.69. This is pressure basically at sea level, which is pretty much what you have here in Manassas. The first law we're going to look at is Boyle's law. It's a law that relates pressure and volume. What happens? As the pressure on a gas increases, the volume of the gas decreases. This relationship is inverse. As one increases, the other decreases. Now, in working problems, the original volume and pressure will be listed as V1 and P1, and the new volume and pressure will be listed as V2 and P2. Remember that the units for P1 and P2 must stay the same, and the units for V1 and V2 must stay the same. We're going to write our givens and our unknowns for every problem. Here's our first example with Boyle's law. There's the formula. P1 V1 equals P2 V2. There's the problem. And we are going to work the problem out first by writing all of our givens. P1 V1, P2 V2. What did the problem give us? Pressure of 2.18 atmospheres and a volume of 3.6 cc's, which are cubic centimeters, a P2 of 742 millimeters of mercury, and we're looking for V2. That's our unknown. Okay, what do you have to notice? You have to notice that the atmospheric, that the pressures are different. The first pressure is in atmospheres, the second pressure is in millimeters of mercury. So we are going to convert millimeters of mercury to atmospheres because we like to work in atmospheres. A lot of problems will be in atmospheres. What's the conversion factor? You have it on the previous slide. Since we want millimeters of mercury to cancel, we put them in the denominator. Atmospheres is what we want, so it's in the numerator, and 1 atmosphere is the equivalent of 760 millimeters of mercury. Get millimeters of mercury to cancel, get your answer in atmospheres, you divide, and sure enough, you have a small atmospheric pressure of 0.976 atmospheres. Notice how much the pressure has decreased. It's decreased from 2.18 to 0.976. What do we expect will happen to the volume? It should increase. Let's see if that's what happens when we do the problem. Using Boyle's law, plug in the numbers given.
Not yet, Mrs. Liebman.
Not yet, Mrs. Liebman. Let's isolate what we're looking for. We're looking for V2. So we're going to divide both sides of the equation by P2. That'll get P2 to cancel. We'll have V2 equal to the expression on the left. Now we will substitute in numbers. P1 is 2.18 atmospheres. V1 is 3.66 cubic centimeters. P2 is 0.76 atmospheres.
Okay, Mrs. Laidman, 0.976 atmosphere.
0.976 atmospheres. And that will be our value for V2. Go ahead. Atmospheres will cancel. We'll have cubic centimeters as our answer. Go ahead and multiply and divide the numbers. Be sure to include units. Okay, what happened? We decreased the pressure. Did our volume increase? Yes, it did. From a little over 3 to a little over 8. Good work. Charles's law. Charles's law relates volume and temperature. As the temperature of a gas increases, the volume of the gas increases. And about this relationship, it is direct. Here's something you have to remember. Every single problem. Temperature must be in Kelvin. Take the Celsius temperature, add 273, and you will have Kelvin. There's Charles's law. V1 over T1 equals V2 over T2. And here's a sample Charles's law problem. Okay, we're given volume, temperature, new volume, looking for a new temperature. Let's solve that problem. First thing, write down all the givens and all the unknowns. V1 is equal to 50.0 meters cubed. T1 is 22.0 degrees Celsius. Uh-oh, got to change it to Kelvin. 273 gives us a Kelvin temperature of 295 Kelvin. V2 is 60.0 meters cubed. T2 is our unknown. Okay. Now, what's happening? Volume is increasing. Therefore, we would expect temperature to increase. Let's solve the problem. There's Charles's law. We have to solve for T2. T2 is in the denominator. So how are we going to isolate T2 and get it in the numerator? I'm going to multiply both sides of the equation by T2. T2 on the right will cancel. Then we have this equation. And we now have to multiply by the reciprocal of the fraction to get T2 alone on the left. Multiply both sides. What happens on the left-hand side? The fractions cancel. We have T2 equaling V2 T1 V1 over V1. Plug in the numbers. 60.0 meters cubed, 295 Kelvin, and 50.0 meters cubed. Meters cubed will cancel. Multiply, divide, and you will have T2. 354 Kelvin. However, the problem did ask us for Celsius, so to go to Celsius, we will subtract 273 from 354, and that will give us a Celsius temperature of 81 degrees Celsius.
Did it work, Mrs. Laitman?
So, what did we predict? We said as the volume increases, the temperature increases. Volume increased, temperature went from 22 degrees Celsius to 81 degrees Celsius. Sure did. Good job, Miss Gill. Avogadro's law. If the pressure and temperature are held constant, then the volume of the gas is directly related to the number of moles of the gas. How? If the number of moles of the gas increase, then the volume increases. N represents the number of moles. The equation is given to you. V1 over N1 equals V2 over N2, and you would solve that just like you solve the Charles's law problem. The next gas law we're going to look at is the ideal gas law, one of my favorite gas laws. It combines all the previous laws together. Pressure, volume, number of moles, temperature, and a constant. PV equals nRT. We call it PIV-NERT. PIV-NERT. R is the gas law constant, and you really need to know two different values for it. 0.021 liter atmosphere moles Kelvin, or 8.31 decimeters cubed kilopascals over moles Kelvin. Notice that what is different is the pressure units. Atmospheres are kPAs. A cubic decimeter and a liter are exactly the same volume. So the only thing that's changed is atmospheres and kilopascals. You must use the 8.31 formula anytime the problem has to do with energy. Anytime you see joules in a problem, because that factor, decimeters cubed kilopascals over moles Kelvin, is equal to joules per mole Kelvin. And joules is a measurement of energy. Okay, that's not going to happen in this problem. We're going to use the 0.831 because we like atmospheres.
We're actually going to use the 0.0821.
And there's your sample problem there. Ideal gas law, what are we going to do? We are going to start by writing what the problem told us for PIV-NERT. We're looking for pressure. Volume is 5.00 liters. N is the number of moles of gas. Uh-oh, they gave us 3.00 grams of sulfur hexafluoride. So we're going to have to convert to moles by knowing the gram formula mass, molar mass of the compound, which Miss Gill speedily looked up. She divided, grams canceled, and we now have moles of the compound. R is 0.0821 liter atmospheres mole Kelvin. Memorize that number. We use it a lot. And temperature is 92.0 degrees Celsius, and we have to change it to Kelvin. 365 Kelvin. There's PIV-NERT. We're solving for pressure, so let's isolate P. Divide both sides of the equation by V. P equals nRT over V. Fill in the numbers. 0.0205 moles. 0.0821 liter atmospheres mole Kelvin. Miss Gill just wrote 0.08201. But we're going to use 0.0821. And T is 265 Kelvin, 365 Kelvin. And V is 5.00 liters. Okay. We will multiply through. Moles will cancel. Kelvin will cancel. Liters will cancel, and we will be left with pressure in atmospheres. Multiply and divide. See what answer you get. We got a pressure of decimal point 123 atmospheres. Okay, you need to know what STP is. STP stands for standard temperature and pressure. What is standard temperature and pressure? Well, it's the temperature and pressure that are listed below. 0 degrees Celsius, or 273 Kelvin, and 1 atmosphere of pressure. And it's important to know that 1 mole of any gas at STP will occupy 22.4 liters. Memorize that. 1 mole of any gas at 0 degrees Celsius and 1 atmosphere of pressure occupies a volume of 22.4 liters. That's a large volume. That is 12 2-liter bottles of soda. All right. Let's do a stoichiometry problem. Stoichiometry is the math related to balanced equations. If the balanced equation has a gas, it can involve gas laws. Gases are involved in reactions and relate to each other through mole ratio. So here's our problem. It's a decomposition problem of calcium carbonate, which is a solid. It's going to produce quicklime, calcium oxide, which is a solid, and carbon dioxide gas. Let's try that problem. What do we do first? It has to do with an equation. We write the equation. Decomposition of calcium carbonate, which is a solid, making the solid calcium oxide plus carbon dioxide gas. Okay. Next, what do we have to do? We have to balance the equation. Ta-da! It's already balanced. So, let's write down what we're given. We're given 152 grams of calcium carbonate, and we're asked to find the volume of carbon dioxide at STP. Okay. So, write down your given, which is 152. And what do we have to do in a balanced equation? Can we use grams? No. We have to convert to moles. 1 mole of calcium carbonate has a molar mass of 100.09 grams per mole. So what does that do? It will get grams of calcium carbonate to cancel. Will give us moles of calcium carbonate. Good. Now we can go from moles of calcium carbonate to moles of carbon dioxide using the coefficients from the balanced equation. Calcium carbonate in the bottom, so it'll cancel, and carbon dioxide in the numerator because it's our unknown, and it's a 1-to-1 ratio. That's the mole ratio from the balanced equation. Now this problem, note the 3 lines underneath STP, this problem is its standard temperature and pressure. And 1 mole of any gas at STP occupies a volume of 22.4 liters. So that gets all our units to cancel, gives us our answer in liters, and our answer is 34.0 liters. There's another way to solve this problem. You could have plugged in standard temperature and standard pressure into PivNert, and with the number of moles, R was the constant, and you would have gotten the exact same volume, 34.0. Try it if you want to. And that is the end of our first gas law lecture. See you tomorrow.